When we use the word universe in physics, we are not speaking casually of the night sky or the stars above. We are describing the totality of space and time, of matter and radiation, and of the fundamental forces that shape them. The universe is everything that can be observed and measured, the great stage on which galaxies evolve, stars ignite, and life briefly flourishes. It includes the smallest quantum fluctuations and the grand sweep of cosmic expansion. Yet despite its immense scale, even this definition comes with a boundary. The boundary is not set by walls of matter, but by the speed of light and the finite age of the cosmos. Light travels at about 300,000 kilometers per second, and because the universe is roughly 13.8 billion years old, there is a maximum distance that light has been able to cover since the beginning of time. Beyond this distance, signals have not had enough time to reach us, no matter how powerful our instruments. This defines the cosmic horizon, also called the observable universe. What lies within this sphere is everything we can in principle observe. What lies beyond is hidden from us forever, not because it does not exist, but because the laws of relativity forbid information from traveling faster than light. The size of this observable universe is immense. Though the universe itself is about 13.8 billion years old, the expansion of space means that the observable region extends about 46 billion light-years in every direction. This is the portion of the cosmos accessible to us, yet it is likely only a small patch of something far larger. Beyond the horizon, space may continue indefinitely, filled with galaxies we will never see, forever separated from us by the vastness of expanding space-time. This boundary raises a profound question. If the universe is defined as all that exists, then why do scientists sometimes speak of other universes or a multiverse? The answer lies in the difference between what exists in principle and what exists in practice for us as observers. Our observable universe is a finite region. There is no guarantee that physics beyond our horizon looks the same. Some models suggest that conditions elsewhere may vary so drastically that it is reasonable to call those regions separate universes. In this way, the concept of a multiverse arises not from fantasy, but from the logical extension of cosmology. The idea that there might be more than one universe is not new. Ancient cultures speculated about multiple worlds long before telescopes or relativity. In India, Hindu philosophy described time as cyclical, with universes born, destroyed, and reborn endlessly. Texts spoke of countless worlds, each with its own cosmic order. In ancient Greece, philosophers like Democritus and Epicurus suggested that an infinite void contained innumerable atoms, forming innumerable worlds. They did not have the data of modern physics, but they shared the intuition that our cosmos might not be unique. Modern science draws a careful distinction, however. Where mythology and philosophy offered imaginative visions, physics builds on evidence. The definition of universe in scientific terms is rooted in observation and measurement. The cosmic horizon is established by light and relativity, not by legend. Yet the echoes of ancient speculation remind us that the human mind has long stretched toward infinity, wondering if existence extends beyond the stars we can see. Today, cosmologists consider the multiverse not because of myth, but because of theory. When models of the early universe are taken seriously, when inflationary expansion is applied to the first fractions of a second, when quantum mechanics is extended to the cosmos as a whole, the possibility of multiple universes appears naturally. These are not added as imaginative ornaments, but as implications of physics already developed to explain what we see within our horizon. The observable universe, then, is not the end of inquiry, but its beginning. To speak of universes beyond ours is to ask whether space continues without bound, whether physical laws vary in other domains, whether the Big Bang was a singular event or one of many. Each of these questions presses against the edges of science. None can be answered directly today, but each motivates a deeper study of the cosmos. The transition from ancient speculation to modern theory is marked by one decisive leap. It is the recognition that the early universe underwent an extraordinary transformation called inflation. Inflation explains why the cosmos is smooth on large scales, why it is flat in its geometry, and why regions separated by great distances share the same initial conditions. In solving these puzzles, inflation also opens the door to the idea of many universes. This is where the scientific multiverse truly begins, not in myth but in mathematics, not in imagination alone, but in the physics of the early universe. The observable universe is a window, and like any window, it both reveals and conceals. What we see is a fraction of what might exist, shaped by the physics of light, the geometry of space, and the flow of time. The galaxies mapped by telescopes such as Hubble and the James Webb are not randomly scattered, but arranged in filaments and clusters, forming a cosmic web that extends as far as we can measure. These patterns emerge from the seeds planted in the earliest instance after the Big Bang, faintly visible in the cosmic microwave background radiation. This glow, discovered in 1965 by Arno Penzias and Robert Wilson, is the afterlight of the early universe, stretched to microwave wavelengths by billions of years of expansion. Its uniformity across the sky is one of the strongest pieces of evidence that the cosmos had a common origin. Yet the very uniformity of this background presents a puzzle. Regions of the sky separated by vast distances look nearly identical in temperature, even though, according to simple Big Bang models, they should never have been in causal contact. If light and information could not travel fast enough to connect them, how did they coordinate their conditions? This is known as the horizon problem. Another mystery lies in the geometry of the universe. Measurements show that space is extremely close to flat, meaning parallel lines remain parallel over cosmological scales. But in standard cosmology, maintaining such flatness requires exquisitely precise tuning of initial conditions. This is called the flatness problem. These paradoxes pressed physicists to search for a mechanism that could explain the observed large-scale properties of the cosmos. In the early 1980s, Alan Guth, a young physicist, proposed the theory of cosmic inflation. According to this idea, the universe, in its first fraction of a second, underwent an unimaginably rapid expansion, growing exponentially in size. Inflation would have stretched out any initial curvature, explaining the observed flatness. It would also have allowed distant regions to originate from the same pre-inflationary patch, solving the horizon problem. In one stroke, inflation provided a framework for understanding why the universe looks as it does today. But like all good theories, inflation did more than solve existing puzzles. It made predictions. Tiny quantum fluctuations during inflation would be stretched to cosmic scales, leaving imprints in the density of matter and radiation. These imprints are visible today in the small variations of the cosmic microwave background. When satellites like COBE, WMAP, and Planck mapped these variations, their patterns matched the predictions of inflation with remarkable precision. The peaks and troughs in the power spectrum of the microwave background, the distribution of hot and cold spots, all supported the idea that inflation had occurred. While no single measurement proves the theory, the convergence of multiple lines of evidence gives it significant weight. Once accepted, inflation carried consequences beyond what Guth originally envisioned. In many models, inflation is not a one-time event that ended everywhere simultaneously. Instead, it continues eternally in some regions, while stopping in others. The regions where it stops form bubble-like universes, each with its own physical laws, while the expansion continues elsewhere. This is called eternal inflation. Our universe would then be one bubble among countless others, each born from the same underlying physics, but potentially differing in the values of fundamental constants, particle masses, or even the number of spatial dimensions. This possibility reframes the word universe. No longer does it simply mean the totality of all existence. Instead, it might mean one finite domain within a larger multiverse. The term multiverse is not an attempt to add mystery, but a recognition that physics may naturally generate multiple universes. The idea does not come from speculation layered on top of science, but from the equations themselves. Once inflation is allowed, the possibility of many universes becomes difficult to avoid. The philosophical weight of this is immense. If universes exist with different physical laws, then our own may be one outcome among many. The strength of gravity, the charge of the electron, the mass of the neutrino values we take as fixed, might vary elsewhere. Some universes might expand too quickly for stars to form. Others might collapse back into singularities almost instantly. A few, like ours, might sustain galaxies, stars, and chemistry long enough for life to appear. This is not speculation for the sake of imagination, but a consequence of applying known physics to the early universe. And yet, caution is vital. The multiverse remains a hypothesis, supported indirectly by inflation, but lacking direct observation. We cannot see beyond our cosmic horizon, and no telescope can peer into another universe. Evidence is indirect, emerging from the consistency of inflation with observed data. As such, scientists must separate what is strongly supported from what is conjectural. The multiverse is an inference, not a proven fact, but it is an inference rooted in equations tested against the cosmic microwave background and large-scale structure. In this way, modern cosmology bridges the gap between the observable and the unobservable. It acknowledges that our data is finite, while our theories point to the infinite. It accepts the limitations of telescopes and detectors, while still daring to consider what may lie beyond. The shift from universe to multiverse is not a rejection of evidence, but an expansion of reasoning. It follows the same pattern that has guided science for centuries, from the Earth as the center of all, to the sun-centered solar system, to the galaxy, to clusters of galaxies, to the observable cosmos. Each time the horizon expanded. Each time what was once thought unique became part of something larger. The question now is whether this pattern continues. If our observable universe is one bubble, are there others? If there are others, how can we classify them? The next step in this story is to move from the broad framework of inflation to the specific ways in which scientists categorize possible multiverses. The most influential system is the one proposed by physicist Max Tegmark, who outlined levels of multiverse, each with its own logic and degree of plausibility. To understand the scope of the idea, we must turn from the cosmic horizon to this structured taxonomy, a map of possibility built not on imagination alone, but on the mathematics of physics. The idea of defining the universe must be handled with precision, because the term has shifted meaning through history. In the earliest human cultures, the universe meant the heavens above and the earth below, a limited stage upon which human life unfolded. The stars were lights in a dome, the planets wandering points, the sun and the moon celestial markers of time. With the advent of telescopes in the 17th century, the universe grew larger. Galileo saw moons around Jupiter. Newton described gravity as a force that acted across space, and gradually the scale of the cosmos expanded. By the 20th century, Edwin Hubble's discovery that galaxies were receding from us revealed that the universe itself was expanding. The universe was no longer static and eternal, but dynamic and evolving, born in a fiery beginning and still stretching outward. At each stage, what people called the universe changed. For some, it meant all of space and time. For others, it meant the observable region accessible to measurement. For still others, it came to mean a bubble within a larger multiverse. This layering of meaning is not a weakness, but a reflection of how science advances. We work with the best definitions we can, refine them as data improves, and accept that our concepts may grow in scope. To define the universe today is to acknowledge that what we see may be one domain within a wider structure. This expansion of perspective does not diminish the significance of our own cosmos. Our observable universe contains more than 2 trillion galaxies, each with hundreds of billions of stars, and likely more planets than grains of sand on all the beaches of Earth. Within this vastness, life has emerged at least once. Here on our small planet, orbiting an average star in the Milky Way. Whether life exists elsewhere, we do not yet know. But already, the scale is staggering. To think that this entire expanse might be one of many universes only deepens the mystery. The multiverse is not an escape into speculation, but a hypothesis born of serious physics. Inflation suggests it. Quantum mechanics hints at branching realities. String theory requires additional dimensions that might host other universes. Mathematics allows for structures beyond what we can observe. None of these ideas is proven, but all arise from the attempt to explain what we do see. The multiverse is therefore a frontier, one that blurs the line between physics and philosophy, between testable science and metaphysical possibility. Skeptics rightly ask how such a concept can ever be tested. If other universes are by definition beyond our cosmic horizon, then what evidence could confirm their existence? The cautious answer is that direct detection may never be possible. But science often deals with indirect evidence. We cannot see the interior of a black hole, but we infer its presence from gravitational effects. We cannot observe quarks directly, but particle collisions reveal their signatures. In the same way, cosmologists search for subtle patterns in the cosmic microwave background, or for anomalies that might hint at collisions between bubble universes in the distant past. The search is ongoing, difficult, and uncertain, but it is guided by the same principles of evidence that shape all science. Meanwhile, the philosophical implications of the multiverse cannot be ignored. If there are countless universes, then the conditions that allow life in ours may not require special explanation. We exist here not because our universe is uniquely tuned, but because we are in one of the rare universes that permits observers. This is the anthropic reasoning often invoked in discussions of the multiverse. It does not satisfy everyone, for it explains by selection rather than mechanism, yet it is consistent with the logic of multiple universes. What remains crucial is the discipline of separating what is known, what is inferred, and what is imagined. We know that our universe is expanding. We know that the cosmic microwave background exists and matches the predictions of inflation. We infer from this that inflation is likely correct. From inflation, we infer that other universes may exist. From there, imagination takes us further, into realms that may never be observed. The boundary between inference and imagination must be kept clear, or science risks drifting into myth. And yet, imagination is not without value. It drives inquiry, inspires hypotheses, and keeps the mind open to possibilities. The multiverse, even if unproven, serves as a reminder that the cosmos may be far stranger and richer than we can presently conceive. Just as ancient thinkers once speculated about multiple worlds and were eventually vindicated by astronomy, perhaps future generations will look back on our age as the dawn of a deeper understanding. For now, we stand at the edge of what can be known. The universe, as we define it, is both vast and bounded, both comprehensible and mysterious. To ask whether it is one of many is to take the next step in a long tradition of expanding horizons. From Earth to solar system, from galaxy to observable universe, the story has always been one of growth. The multiverse is the latest chapter in this story, an attempt to describe the ultimate scope of reality. The origins of this idea lie in the physics of the early cosmos. The Big Bang, once thought to be the single birth of everything, may instead be one event in an eternal sequence of inflating regions. The mathematics of inflation provides a bridge from the known to the possible, from the universe we observe to the multiverse we infer. And so, the transition is clear. To move from defining the universe to exploring the multiverse, we must follow the path of inflation. It is inflation that offers the first scientific foundation for multiple universes, and it is there that our journey continues. In the earliest moments of the cosmos, fractions of a second after the Big Bang, the universe was unimaginably hot and dense. Particles, radiation, and quantum fields were intertwined in a state beyond anything that can be recreated in laboratories today. According to the standard Big Bang model, this state expanded and cooled, eventually forming protons, atoms, stars, and galaxies. Yet as powerful as the Big Bang framework is, it leaves critical puzzles unresolved. It does not explain why the universe is so uniform across vast distances, why space is so nearly flat in its geometry, or why relics predicted by high-energy physics, such as magnetic monopoles, are not observed. In 1981, Alan Guth, a young theoretical physicist, proposed a solution that would reshape cosmology. He suggested that in the first tiny fraction of a second, the universe underwent a brief but extraordinary period of exponential expansion, growing by an enormous factor in an instant. This idea was called cosmic inflation. During inflation, space itself expanded faster than light, not violating relativity, because relativity limits the speed of objects moving through space, not the stretching of space itself. This expansion smoothed out irregularities, flattened curvature, and diluted unwanted relics. In one stroke, it solved the horizon problem, the flatness problem, and the relic problem. The horizon problem is perhaps the most striking. Regions of the sky that are now billions of light years apart show nearly identical temperatures in the cosmic microwave background radiation. Without inflation, there is no way these regions could have exchanged information or energy, because light could not have traveled far enough in the time available. With inflation, however, these regions were once close together, in causal contact, before the rapid expansion pushed them apart. Their similarity today is therefore no longer mysterious. The flatness problem is equally compelling. Observations show that the universe's geometry is extremely close to flat, meaning that the overall density is almost exactly equal to the critical density. Without inflation, maintaining this balance over billions of years would require an almost impossible fine-tuning of initial conditions. With inflation, any initial curvature would have been stretched away, like the surface of an inflating balloon, appearing flatter as it grows larger. Inflation thus provides a natural mechanism for the observed flatness of the cosmos. The relic problem involves hypothetical heavy particles predicted by grand unified theories. Without inflation, these relics should be abundant, yet none are detected. Inflation, by diluting their density exponentially, explains their absence. This solution, while less central than the horizon or flatness problems, adds to the consistency of the theory. Like all powerful ideas, inflation made predictions that could be tested. Quantum fluctuations, tiny variations in energy fields at the microscopic scale, would have been stretched to cosmic sizes during inflation. These fluctuations seeded the large-scale structure of the universe, giving rise to the distribution of galaxies and clusters we see today. They also left imprints in the cosmic microwave background radiation, visible as small temperature variations across the sky. Satellite missions such as COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s measured these variations with increasing precision. The results matched the predictions of inflation remarkably well. The pattern of peaks in the power spectrum, the statistical distribution of hot and cold spots, and the overall scale invariance of the fluctuations all align with what inflation forecasts. This agreement between theory and observation transformed inflation from a speculative idea into a central element of cosmology. While details of how inflation occurred remain debated, the basic concept is widely accepted. The mechanism that drove inflation is thought to be a field of energy, sometimes called the inflaton, which dominated the dynamics of the early universe. As the field decayed, inflation ended, releasing energy that reheated the universe and filled it with the particles and radiation that would later form stars and galaxies. Yet inflation did more than solve puzzles and make predictions. It opened the door to a radical possibility. In many models, inflation is not something that ends everywhere at once. Instead, it ends in some regions while continuing in others. The regions where it ends form expanding bubbles, each evolving into a universe like ours, while inflation carries on indefinitely elsewhere. This scenario is called eternal inflation. The multiverse, in this framework, is not a speculative add-on, but a natural consequence of the equations. If inflation is correct, it may inevitably produce multiple universes. These bubble universes are not separated by empty space, but by inflating space itself. Each bubble expands, potentially containing galaxies, stars, and life. The properties of each bubble may differ depending on the details of how inflation ended there. In some, the values of fundamental constants could vary, leading to universes with different physical laws. Some might expand too rapidly for structure to form, others might collapse quickly, and a few, like ours, might have conditions suitable for complexity. This landscape of possibilities transforms the idea of cosmology. No longer is the question simply why our universe has the properties it does. The deeper question is whether our universe is just one of many outcomes in a grander cosmic ensemble. The possibility of eternal inflation marks a profound transition. From the attempt to explain why our universe looks the way it does, physics is led to consider that there may be countless other universes, forever beyond our horizon. This does not mean that such universes are proven to exist, but it does mean that their existence is a serious implication of a theory that already explains what we see. It is here, in the mathematics of exponential expansion, that the modern scientific concept of the multiverse begins. Inflation as a theory did not emerge in isolation. It grew from decades of effort to unify particle physics with cosmology. The notion that the universe could be dominated by a special energy field came from attempts to explain why fundamental forces appear distinct today, but may have been unified in the earliest moments after the Big Bang. Grand unified theories predicted that at unimaginably high energies, the electromagnetic, weak, and strong nuclear forces were one. As the universe cooled, these forces separated. Inflation offered a natural stage for this separation, driven by the dynamics of a scalar field that temporarily trapped the universe in a high-energy state. Alan Gough's first model of inflation, though powerful, had shortcomings. It ended too abruptly and produced irregularities inconsistent with observations. Other physicists refined the idea. André Linde proposed what he called chaotic inflation, in which inflation could occur in many regions of space, with different initial conditions. Paul Steinhardt and Andreas Albrecht developed new inflation, where the inflaton field rolled more smoothly toward its minimum. These refinements not only made inflation more consistent with data, but also broadened its implications. In particular, Linde's chaotic inflation became the foundation for the idea of eternal inflation. In eternal inflation, the decay of the inflaton field is not uniform. Some regions of space transition to the lower energy state that ends inflation, while others remain stuck in the higher energy state, continuing to inflate. Because inflation is exponential, regions that keep inflating grow faster than regions that stop. The result is that inflation never truly ends everywhere. It produces an infinite fractal-like structure of bubbles, each expanding and evolving as its own universe, while the background continues to inflate. Our observable universe would then be one bubble among countless others. This picture may sound extraordinary, but it arises naturally from the mathematics. The quantum fluctuations of the inflaton field mean that in some regions, it decays quickly, in others slowly, and in still others hardly at all. Randomness at the quantum level drives an infinite proliferation of universes at the cosmic level. This is one of the most striking examples of how quantum mechanics and cosmology intertwine. What is uncertain in the microscopic becomes decisive in the macroscopic, shaping the very structure of existence. If eternal inflation is correct, then the multiverse is populated by bubbles with potentially diverse properties. The physical constants we measure in our universe may not be universal at all, but local. The fine structure constant, which governs the strength of electromagnetism, or the cosmological constant, which drives accelerated expansion, could take different values in different bubbles. Even the number of spatial dimensions might vary in some exotic scenarios. The multiverse then becomes a cosmic laboratory, with each bubble a different experiment in physics. We find ourselves in a bubble compatible with life, because only such bubbles can host observers. This line of reasoning is called anthropic selection. It does not predict the exact values of constants, but explains why we observe values that permit complexity. This perspective challenges the traditional ambition of physics to derive unique, inevitable laws of nature. If constants vary across the multiverse, then the laws we measure may be environmental rather than fundamental. They are what they are, because we are here to measure them, not because they are uniquely determined. Some scientists accept this shift as a natural consequence of inflation. Others resist it, arguing that it undermines the explanatory power of science. The debate remains active, reflecting the deep philosophical consequences of inflationary cosmology. Evidence for inflation itself remains strong, even if eternal inflation remains speculative. The cosmic microwave background radiation contains patterns that match inflation's predictions, such as the nearly scale-invariant spectrum of fluctuations. Large-scale surveys of galaxies also reveal clustering consistent with inflationary seeds. One of the most sought-after signatures is a particular pattern of polarization in the microwave background called B modes, which would indicate primordial gravitational waves generated during inflation. In 2014, the BICEP-2 experiment initially reported such a detection, but later analysis showed the signal was dominated by galactic dust. The search continues with more sensitive instruments, for a true detection would be a landmark confirmation of inflation. Even without this, the success of inflation in explaining multiple puzzles makes it the leading theory of the early universe. It provides a coherent narrative linking quantum fluctuations, cosmic structure, and the uniformity of the microwave background. It is not perfect. Many versions of inflation exist, and the exact nature of the inflaton field remains unknown. Some physicists explore alternatives, such as bouncing cosmologies or ekpyrotic scenarios inspired by string theory. Yet inflation endures because of its elegance and its compatibility with data. From the perspective of the multiverse, inflation is not simply a historical episode, but an ongoing process. Somewhere, in distant regions forever beyond our view, inflation continues, even now. New bubbles form, new universes begin, each with its own potential history. This is not poetic metaphor, but a literal implication of the mathematics if eternal inflation is correct. The cosmos is then not a single unfolding, but an endless branching, a tree of universes growing without end. This vision transforms our place in reality. Our observable universe, vast though it is, becomes a local phenomenon. The cosmic horizon, 46 billion light-years away, is not the edge of existence, but the edge of what we can see. Beyond it, other universes may expand, shaped by physics we cannot yet measure. To think in these terms is to step beyond the boundaries of conventional science, but it is also to remain faithful to the logic of theory and evidence. Inflation leads us here. It compels us to consider the multiverse as more than speculation, as a framework consistent with the equations that already explain so much. The story of inflation, then, is twofold. On one hand, it is a triumph of physics, solving long-standing puzzles and making predictions confirmed by observation. On the other, it is an opening to the possibility of multiple universes, forever beyond our reach, yet born from the same physics that describes our own. To explore this possibility more fully, scientists have attempted to classify the different kinds of multiverses that might exist, distinguishing what is plausible from what is speculative. This brings us to one of the most influential frameworks in the modern discussion, the hierarchy of multiverse levels, proposed by Max Tegmark. Inflation's deepest consequence is that it shifts the question of uniqueness. Before the theory, cosmologists sought to explain why the universe had the particular conditions we observe. After inflation, the possibility arises that these conditions are not unique, but one set among countless others. Eternal inflation in particular suggests that universes are being born continuously, each with its own set of constants and outcomes. In such a picture, what appears fine-tuned in our universe may not require explanation at all, because in the multiverse, every possibility occurs somewhere. We happen to exist in one of the rare universes where the conditions allow for stars, chemistry, and life. This line of thinking, though controversial, has a precedent in the history of science. For centuries, Earth was thought to be the center of the cosmos, uniquely suited for life. The Copernican revolution displaced Earth, revealing it as one planet among many. Later telescopes revealed that the Sun is one star among hundreds of billions in the Milky Way, and that our galaxy itself is one among trillions in the observable universe. Each time, the special status of our location diminished. The multiverse, if real, would be the next step in this progression. Our universe would be one of countless universes, not privileged, but typical, in a much larger ensemble. Yet this vision must be balanced against the scientific demand for evidence. The strength of inflation lies in its predictions within our universe. The weakness of the multiverse lies in its potential untestability. No matter how powerful our instruments, we cannot see beyond the cosmic horizon, because light from beyond it has not had time to reach us. Other universes, if they exist, may be forever inaccessible. This raises a dilemma. Is a scientific theory valid if it predicts entities that can never be observed? Some argue that indirect evidence, such as imprints of bubble collisions on the cosmic microwave background, could one day reveal the influence of other universes. Others argue that even without direct detection, the multiverse remains a legitimate implication of inflation, as long as the underlying theory is supported by data. This debate highlights a subtlety about the philosophy of science. Physics has always dealt with unobservable entities, from quarks to neutrinos to gravitational waves, before they were directly detected. The difference is that those entities eventually became testable. With the multiverse, the barrier may be permanent. The horizon is not a technological limitation, but a fundamental feature of space-time. This makes the question more difficult. How should science handle possibilities that are mathematically consistent and physically motivated, but observationally unreachable? The answer is still being shaped by ongoing debates among physicists and philosophers. For now, inflation remains the most successful theory of the early universe, and the multiverse remains its most dramatic implication. Observational efforts continue, from searches for B-mode polarization to measurements of the large-scale distribution of galaxies. Each new dataset refines our understanding of inflation's parameters. Each refinement helps clarify whether eternal inflation is inevitable or avoidable. The outcome will shape whether the multiverse remains a serious scientific hypothesis or fades into speculation. Regardless, inflation has already transformed cosmology. It has shown that the universe we observe is consistent with a deeper and more dynamic story. It has revealed that the seeds of galaxies were quantum fluctuations magnified to cosmic scales. It has demonstrated that the smoothness and flatness of the cosmos are natural outcomes of early expansion, and it has opened the door to one of the boldest ideas in science, that our universe may be one of many. This door cannot easily be closed. Even if alternatives to inflation are developed, many also predict multiple universes. String theory, for example, suggests a vast landscape of possible vacua, each with its own physical constants, corresponding to different universes. Quantum mechanics, as we will see, has its own many worlds interpretation, in which every quantum choice branches into new realities. These diverse paths converge on the same unsettling possibility. Reality may be far larger than the universe we know, and so the story of inflation brings us to the threshold of classification. If there may be multiple universes, how do we organize the concept? How do we distinguish between different kinds of multiverse hypotheses, from those grounded in well-established physics to those that verge on the philosophical? To answer this, We turn to the work of Max Tegmark, who proposed a hierarchy of multiverse levels. Each level represents a different way in which multiple universes could exist, ranging from the simple extension of space beyond our horizon to the radical possibility that reality itself is mathematical. The transition is clear. From the expansion of space in the first instant after the Big Bang, we are led to the idea of eternal inflation. From eternal inflation, we are led to the multiverse. And from the multiverse, we are led to its classification into distinct levels. The journey continues, not as speculation detached from science, but as the unfolding of logic from the physics of the early universe. If inflation suggests that multiple universes may exist, the next step is to ask how we might categorize such a possibility. A theory as expansive as the multiverse risks becoming vague unless it is framed with precision. One of the most influential attempts to bring order to the discussion comes from physicist Max Tegmark, who proposed that there are distinct levels of multiverse, each defined by a different physical principle. These levels range from the relatively modest idea of space extending beyond our horizon to the radical notion that reality itself is purely mathematical. Though some levels are widely accepted and others highly speculative, the framework offers a way to organize thinking about the multiverse and to separate scientific plausibility from philosophical extension. The first level of Tegmark's classification, level 1, is in some ways the least controversial. It states simply that space continues beyond what we can observe. Our observable universe is bounded by the cosmic horizon, about 46 billion light-years in radius. But there is no reason to think that space ends there. The same physical laws that apply here should apply beyond, and galaxies should continue indefinitely. If space is infinite, then the multiverse of level 1 is simply the infinite continuation of what we see. The only difference between us and regions beyond the horizon is that we cannot communicate across such vast distances. Level 1 requires no new physics beyond the assumption that the cosmos extends further than we can see. Within an infinite space, however, strange consequences emerge. Given enough volume, the arrangement of particles in any region will eventually repeat. There may be distant regions of space where conditions mirror our own, down to exact duplicates of Earth and of ourselves, separated by distances so immense that no signal could ever bridge them. This is not science fiction, but a statistical property of infinity. If the cosmos is infinite, then every configuration occurs somewhere. While this is difficult to imagine, it follows directly from the mathematics of probability. Level 2 of Tegmark's framework builds directly on the concept of eternal inflation. In this level, the multiverse is composed of bubble universes, each created when inflation ends in a region of space. The key difference from level 1 is that in level 2, the physical constants may vary between bubbles. The vacuum state into which inflation decays can differ, leading to universes with distinct laws of physics. In one bubble, the cosmological constant may be large, causing rapid expansion that prevents galaxies from forming. In another, gravity may be stronger, leading to rapid collapse. Only in a small subset of bubbles do the constants fall within the narrow range that allows complexity and life. We find ourselves in such a bubble, not because it is typical, but because only in such bubbles can observers exist. This anthropic reasoning is often controversial, but within level 2, it arises naturally. If there are countless universes with different constants, then the fact that we observe a life-permitting universe is not surprising. It is not that the universe was designed for life, but that life can only arise in universes where conditions allow it. The multiverse of level 2 thus provides a potential explanation for the apparent fine-tuning of physical constants without invoking deeper necessity or design. Evidence for level 2 multiverses is indirect, as it relies on the plausibility of eternal inflation. Inflation itself is well supported, but eternal inflation remains more speculative. Still, the framework is logically consistent. If inflation occurs, and if it is eternal, then level 2 universes follow. In this sense, level 2 is not an independent hypothesis, but a consequence of inflationary theory. These first two levels already cover much of what cosmologists mean when they speak of the multiverse. Level 1 is an infinite cosmos beyond our horizon. Level 2 is a set of bubble universes with varying constants. Both arise from well-established physics. The next levels, however, are more controversial, as they involve quantum mechanics and mathematics at their deepest levels. To approach them, we must first understand how quantum theory itself suggests the existence of multiple universes. Level 3 of Tegmark's classification takes us from the cosmology of inflation into the foundations of quantum mechanics. Quantum theory describes the world of the very small, where particles can exist in superpositions of states, waves of probability until measured. The traditional Copenhagen interpretation holds that when a measurement occurs, the wave function collapses, and one outcome becomes real, while all others vanish. But in 1957, Hugh Everett proposed a radical alternative. According to his many worlds interpretation, the wave function never collapses. Instead, all possible outcomes occur, each in a separate branch of reality. In this view, when an electron is measured and could be found spin up or spin down, both outcomes happen. The universe splits into two, one where the electron is spin up, one where it is spin down. Every quantum event branches the universe into multiple copies, each containing observers who see one outcome and not the others. This branching happens constantly with every interaction of particles, so that the cosmos is endlessly dividing into parallel realities. The multiverse of level 3 is therefore not spatially separated bubbles, but quantum branches, coexisting in a higher level reality. This interpretation has startling consequences. In level 3, there is a version of you that made every choice differently, a version that lives in a slightly different world created by quantum outcomes. These universes are not somewhere else in space, as in level 1 or level 2, but exist as parallel branches of the same underlying quantum state. The mathematics of quantum mechanics is entirely consistent with this picture, and in fact some argue that it is simpler than the Copenhagen view, because it requires no special rule for wave function collapse. The Schrödinger equation, which governs the evolution of the wave function, is deterministic and universal. To get collapse, one must add something by hand. To get many worlds, one simply accepts the mathematics as written. But while elegant in theory, the many worlds interpretation remains controversial. It predicts no new observable consequences beyond those of quantum mechanics itself. Whether collapse is real or all outcomes occur in branching universes, the probabilities we calculate are the same. Experiments confirm the probabilities with exquisite precision, but they do not distinguish between interpretations. The question of whether level 3 multiverses exist, therefore, rests not on data, but on philosophical preference. Do we accept collapse as a special rule, or do we embrace branching as the natural consequence of the equations? Some physicists object that many worlds multiply reality without necessity. Others counter that the alternatives are even more complicated, invoking ad hoc rules to explain measurement. The debate is unresolved, and perhaps unresolvable, at least with current knowledge. Still, the many worlds interpretation has gained traction in recent decades, both for its internal consistency and for its bold vision of reality. If it is correct, then quantum mechanics itself ensures that the universe we see is one among countless parallel universes, differing at every moment. In Tegmark's framework, level 3 is distinct from level 1 and level 2, but not entirely separate. In fact, the set of outcomes realized in level 3 may be equivalent to the diversity of universes in level 1 and level 2. The branching of quantum events within one bubble universe could reproduce the variety of possibilities found across bubbles. In this sense, the different levels may overlap, describing the same idea in different languages. Beyond level 3 lies the most speculative level of all. Level 4 is not about space beyond our horizon, nor bubbles from inflation. nor quantum branches. It is about the nature of reality itself. Tegmark proposed that mathematics is not just a tool to describe reality, but that reality is mathematics. In level 4, every mathematically consistent structure exists as its own universe. Our universe is one such structure, defined by the equations of physics we observe. Other universes exist wherever mathematics allows them, regardless of whether they resemble our own. This is the most radical extension of the multiverse idea, and the one most debated. Level 4, the final stage of Tegmark's hierarchy, is not based on inflation or quantum mechanics, but on a philosophical leap. It begins with the observation that the physical laws of our universe can be expressed in mathematical form. From Newton's laws of motion to Einstein's equations of relativity to the quantum field equations of the Standard Model, mathematics is the language of physics. Tegmark asked whether this correspondence is more than descriptive. What if mathematics is not just a tool we use to describe the universe, but the substance of the universe itself? If so, then every mathematical structure should exist as a universe. Our cosmos is one mathematical object among infinitely many, each with its own consistent rules. In this view, the multiverse is as vast as mathematics itself. A universe might be defined by a set of equations we can recognize, or by structures entirely foreign to human understanding. Some universes might resemble ours, with space-time, particles, and forces. Others might have no notion of space or time at all, existing in frameworks that cannot be visualized. The mathematical multiverse is therefore the most expansive and radical, encompassing all possible realities that mathematics allows. Supporters of level 4 argue that it offers a final explanation. If every mathematical structure exists, then there is no question why our universe has the laws it does. It simply does because those laws correspond to one structure among many. There is no deeper reason. The multiverse of level 4 eliminates the need for ultimate explanation by making every possibility real. This perspective appeals to those who see physics as inseparable from mathematics and who value parsimony in avoiding special exceptions. Critics respond that this level goes beyond science. It is not testable and may never be. While level 1 follows from spatial extension, level 2 from inflation, and level 3 from quantum mechanics, level 4 rests on an abstract philosophical stance. Its boldness is undeniable, but so is its distance from empirical verification. For some, it is an intriguing idea that belongs in the realm of metaphysics. For others, it is a natural extension of the long history of physics describing reality through mathematics. Taken together, the 4 levels of Tegmark's framework create a spectrum. Level 1 is widely accepted, requiring only that space extend beyond our horizon. Level 2 is plausible, supported by inflationary cosmology, though eternal inflation remains unproven. Level 3 is debated, but grounded in the mathematics of quantum theory. Level 4 is the most radical, shifting from physics to philosophy. By placing them on this spectrum, we can see that the multiverse is not a single idea, but a layered concept, with varying degrees of evidence and controversy. The classification does more than organize hypotheses. It highlights the continuity of thought across disciplines. Inflation, quantum mechanics, and mathematics are not separate silos but interwoven threads, leading to the same question: is our universe unique? Each level offers a different way to answer no. If space is infinite, then countless universes exist beyond our view. If inflation is eternal, then countless bubbles form across space-time. If quantum mechanics branches, then countless outcomes are realized in parallel. If mathematics is reality, then countless structures exist, each a universe in its own right. The scientific community views these levels with different degrees of seriousness. Level 1 is almost trivial. Level 2 is plausible. Level 3 is debated, but respectable. And level 4 is largely philosophical. Still, the act of classification matters, because it shows that the multiverse is not a monolith. It is a family of ideas, some close to observation, some far from it. To engage with the multiverse responsibly, we must keep these distinctions clear. Otherwise, the word risks meaning everything and nothing at once. Having framed the multiverse in this way, the next step is to explore the level most directly tied to physics experiments. Level 3, the many worlds interpretation of quantum mechanics. Unlike inflation, which draws on cosmological data, the many worlds hypothesis arises from the mathematical structure of quantum theory itself. It does not involve galaxies or cosmic horizons, but particles, probabilities, and measurements, yet its implications are just as vast. To understand the multiverse through the lens of quantum mechanics, we must turn to the strange world where observation itself plays a role in shaping reality. The story of the multiverse takes a new turn when we enter the domain of quantum mechanics. Unlike cosmology, which deals with galaxies and the structure of space-time, quantum theory describes the microscopic world of atoms and particles. It is here that the rules of reality seem most alien to common sense. Particles exist in superpositions, occupying multiple states at once. Outcomes are described by probabilities rather than certainties. Observation appears to play a fundamental role in determining what is real. These features have puzzled scientists for more than a century, and they are central to the connection between quantum theory and the multiverse. At the heart of quantum mechanics lies the wave function. The wave function is a mathematical object that encodes all possible states of a system and their probabilities. For a simple particle, the wave function tells us the likelihood of finding it here or there, moving slowly or quickly. For larger systems, the wave function can describe vast numbers of possibilities at once. Before observation, the system exists in a superposition of all these states. When we measure it, we find one outcome. The mystery is why. In the traditional Copenhagen interpretation, the wave function collapses upon measurement. All possibilities, except one, vanish, and the chosen outcome becomes reality. Collapse is not described by the equations of quantum mechanics themselves. The Schrödinger equation, which governs the wave function's evolution, is smooth and deterministic. Collapse must be added as a separate rule, triggered by observation or measurement. This makes the observer a central part of the theory, a position that many scientists have long found troubling. Hugh Everett, a graduate student at Princeton in the 1950s, proposed a bold alternative. He argued that the wave function never collapses. Instead, it evolves according to the Schrödinger equation at all times, encompassing all possible outcomes. When a measurement occurs, the observer becomes entangled with the system, and the universe branches. In one branch, the observer sees outcome A. In another branch, the observer sees outcome B. Both branches are equally real, each containing a copy of the observer who remembers only their outcome. This idea became known as the many worlds interpretation. In Everett's view, the apparent randomness of quantum mechanics arises not because outcomes are destroyed, but because observers find themselves in one branch rather than another. All outcomes happen, but each is confined to its own world. The probabilities we calculate reflect the distribution of outcomes across branches, not the destruction of possibilities. The universe is constantly splitting, not in the sense of tearing apart, but in the sense that the wave function encompasses more and more branches as time goes on. This interpretation removes the special role of the observer. There is no collapse, no mysterious boundary between quantum and classical. The mathematics is applied universally, from electrons to people to galaxies. The cost is that we must accept the existence of countless parallel realities. Every quantum event that could happen does happen, and we live in only one thread of that vast branching structure. It is a picture of reality that is at once elegant in its mathematics and astonishing in its implications. The many worlds interpretation remained obscure for decades. Everett's work was not widely appreciated during his lifetime, and he left academia soon after proposing it. Only later did physicists such as Bryce DeWitt and others revive the idea and explore its consequences. Today, Many worlds is one of several interpretations of quantum mechanics, alongside Copenhagen, pilot wave theory, objective collapse models, and others. No experiment has yet distinguished between them, because they all predict the same observable probabilities. The debate is therefore not about data, but about how to understand the mathematics. Still, many worlds has gained traction, especially among those who value mathematical simplicity. The Schrödinger equation applies universally, with no need for extra rules. The interpretation is deterministic at the level of the wave function, with probabilities emerging from the branching structure. To many, this is a more coherent picture than collapse, which introduces ambiguity about what counts as a measurement and when collapse occurs. The appeal of many worlds lies in its refusal to compromise with mystery. It takes the equations literally, no matter how strange the consequences. The implications extend far beyond physics. If every quantum possibility occurs in some branch, then there are versions of history where every alternative path is realized. There are universes where you made every choice differently, universes where events turned out in every possible way. These are not science fiction stories, but literal consequences of the mathematics if many worlds is correct. The multiverse of quantum mechanics is vast, not in space, but in branching possibility. And yet, skepticism is justified. Many worlds is elegant, but untestable. If we cannot access other branches, then how can we know they exist? Critics argue that multiplying universes without evidence violates the spirit of science. Supporters reply that refusing to accept the mathematics as written is more of a violation, adding collapse by hand when the equations do not require it. The dispute is not settled, and may not be, unless new insights into quantum mechanics emerge. The connection to the broader multiverse debate is clear. Just as inflation leads to bubble universes, quantum mechanics may lead to branching universes. Both expand our concept of reality beyond what we can observe. Both raise questions about testability and philosophy. And both suggest that our universe is not unique, but one among many. To grasp how deeply quantum mechanics challenges our view of reality, we must now follow the consequences of Everett's idea further, into the details of entanglement, probability, and the strange role of the observer. The core of the many worlds interpretation rests on entanglement. When a quantum system interacts with another system, their wave functions become linked or entangled, so that the state of one cannot be described independently of the other. Imagine a particle in a superposition of two possible states, and an observer measuring it. According to many worlds, the observer becomes entangled with the particle. In one branch, the observer records outcome 1. In another branch, the observer records outcome 2. The branching does not stop there. The environment, the measuring device, and every atom involved all become part of the entangled wave function, spreading the branching outward into the universe. This process is called decoherence. Decoherence explains why quantum superpositions are not visible in everyday life. On microscopic scales, particles can exist in multiple states at once, but as soon as they interact with their environment, the superposition spreads into a vast entangled web of possibilities, each branch evolving independently. The result is that each branch looks classical, with definite outcomes, even though the underlying wave function never collapsed. From the inside, observers experience a single world. From the outside, the mathematics describes a branching tree of worlds. Probability in this framework is subtle. If all outcomes occur, what does it mean to say that one outcome is more probable than another? In standard quantum mechanics, the probabilities are given by the Born rule, which says that the chance of observing a particular outcome is proportional to the square of the amplitude of that outcome in the wave function. In many worlds, all outcomes happen, so probability must be reinterpreted. One way to understand it is through the idea of self-location uncertainty. Before a measurement, an observer knows that they will split into multiple copies. The probabilities describe the likelihood of finding oneself in one branch rather than another. The Born rule emerges as a measure of how much of the wave function is devoted to each outcome. Though this reasoning is debated, it shows how probability can retain meaning even when all outcomes occur. The elegance of this picture is that it removes the arbitrary boundary between quantum and classical. In the Copenhagen interpretation, one must specify when collapse occurs. But the line between microscopic and macroscopic is vague. In many worlds, no such line exists. The equations apply universally. What we call classical reality is simply what it looks like inside one branch. The consistency of physics across scales is preserved, and the strange role of the observer is dissolved. Observers are just physical systems, subject to the same rules as everything else. Still, critics argue that many worlds raises more questions than it answers. If every outcome happens, why do we experience only one? What distinguishes the experience of a single branch from the mathematical totality of all branches? Some suggest that consciousness itself may be tied to branching, but this enters philosophical territory beyond physics. Others argue that without a mechanism for probabilities beyond interpretation, the theory risks becoming incomplete. Many worlds remains an elegant but controversial solution to the quantum puzzle. The implications for the multiverse are profound. Level 3 multiverses, the many worlds branches, differ from Level 1 and Level 2 universes. The bubbles of eternal inflation are spatially separate, vast regions of spacetime never in contact. The branches of many worlds are not separate in space, but coexist within the same universal wave function. They are parallel realities rather than distant ones. This distinction matters because it shows that the multiverse is not a single concept, but a convergence of different theories. Inflation and quantum mechanics, though very different, both lead us to multiple universes. Comparing many worlds to other interpretations helps clarify why it is taken seriously. Pilot wave theory, proposed by Louis de Broglie and later developed by David Bohm, restores determinism by positing hidden variables that guide particles along definite paths. Objective collapse models, such as the GRW theory, modify the Schrödinger equation so that wave functions collapse spontaneously at random intervals, avoiding branching. Each interpretation has strengths and weaknesses. Pilot wave theory preserves determinism, but introduces hidden variables with no direct evidence. Collapse models add new physics but are constrained by experiments that have not yet detected deviations from standard quantum mechanics. Many worlds avoids collapse and hidden variables, but demands that we accept a proliferation of universes. What makes many worlds compelling is not that it is proven, but that it is mathematically clean. The equations of quantum mechanics are taken at face value, without modification. For some physicists, this is enough reason to prefer it, even if the price is a multiverse of branching worlds. For others, the price is too high, especially since the branches may never be observed. The debate is ongoing, and may continue as long as quantum mechanics remains resistant to experimental distinctions between interpretations. Yet the idea of branching universes has captured more than the attention of physicists. It has inspired writers, filmmakers, and philosophers to imagine parallel realities in which every choice and chance event plays out. In this way, many worlds has become part of the cultural imagination, blurring the boundary between science and story. But at its core, it remains a serious attempt to solve one of the deepest puzzles in physics. Whether it is correct or not, it forces us to confront the strangeness of quantum mechanics in its full intensity. Quantum mechanics has always demanded humility. Its equations are precise, its predictions extraordinarily accurate, but its interpretation remains unsettled. The many worlds interpretation is one response to this uncertainty. By eliminating collapse and embracing branching, it offers a picture of reality that is consistent, deterministic at the level of the wave function, and complete in its mathematics. What it lacks is direct evidence. The other branches cannot be accessed. No experiment has shown collapse to fail, nor has any detected the presence of parallel realities. This absence of evidence is why many worlds remains an interpretation, not a proven fact. Nevertheless, the idea illustrates how deeply quantum theory reshapes our concept of reality. The universe we experience is not necessarily the whole. At every moment, the wave function encompasses countless possibilities. We live in one branch, but the mathematics allows for many. This branching is not science fiction added onto physics, but physics taken literally. Equations followed to their logical conclusion. That is the strength of the many worlds perspective, even if it leads to uncomfortable implications. Some physicists argue that we should not worry about interpretation. Quantum mechanics works, and its predictions match experiment to extraordinary precision. The debate over collapse versus branching may therefore be philosophical rather than scientific. Others reply that interpretations matter because they shape how we think about the future of physics. If many worlds is true, then the multiverse is built into the foundations of reality. If collapse is true, then there is a boundary we do not yet understand. If hidden variables exist, then a deeper layer of physics is waiting to be discovered. Each interpretation implies a different vision of the cosmos. The cultural resonance of many worlds is a reminder of how powerful its imagery is. The thought that every choice leads to a branching universe speaks directly to human imagination. It suggests that there are worlds where history unfolded differently, where wars were avoided, where discoveries were made earlier or later, where lives turned out along different paths. While these speculations go far beyond science, they echo the central idea. Reality may be larger and more complex than the single world we perceive. In the broader framework of the multiverse, Level 3 universes complement the universes of Levels 1 and 2. They do not require eternal inflation or infinite space. They arise from the mathematics of quantum mechanics itself. If the wave function is universal and never collapses, then many worlds follow. This makes quantum mechanics one of the most direct links between established physics and the idea of multiple universes. Still, caution is essential. The many worlds interpretation does not predict anything that standard quantum mechanics does not. Experiments on entanglement, superposition, and interference all agree with quantum theory, but none distinguish between interpretations. That means the question of whether branching universes exist may remain forever outside empirical reach. This limitation does not disqualify the idea from serious discussion, but it does place it in a category different from theories that can be tested directly. The strength of the many worlds interpretation lies in its simplicity. The Schrödinger equation is universal. There is no collapse, no hidden variables, no special exceptions for measurement. The price is that we must accept a vast branching multiverse. Whether this price is too high depends on one's view of science. For some, the proliferation of universes is extravagant. For others, it is simply the mathematics taken seriously. In either case, it is a profound shift in perspective, extending the concept of the multiverse from cosmology into the quantum domain. The journey does not stop here. Beyond inflation and quantum mechanics lies another frontier, string theory and M theory, which suggests that our universe may not only be one among many, but that it may exist as a brain in a higher dimensional space. These ideas, like many worlds, are speculative, but they are grounded in attempts to unify the laws of physics. If correct, they expand the multiverse once again, this time into higher dimensions. To follow the story, we must now move from the quantum world to the realm of strings, brains, and extra dimensions. If quantum mechanics reveals that our universe may branch into parallel realities, string theory suggests that our universe itself may be only one sheet in a higher dimensional landscape. Where many worlds arises from interpreting the mathematics of the quantum wave function, string theory arises from the effort to unify the forces of nature into a single, consistent framework. At its core lies a radical idea that the most fundamental entities in the universe are not point-like particles, but tiny vibrating strings of energy. The different modes of vibration give rise to different particles, just as different vibrations of a violin string produce different notes. This picture began in the 1970s as a mathematical attempt to reconcile quantum mechanics with gravity, the one fundamental force not included in the standard model of particle physics. Quantum field theory works well for electromagnetism and the nuclear forces, but breaks down when applied to gravity at very small scales. Calculations produce infinities that cannot be renormalized. String theory, by replacing point particles with one-dimensional strings, smooths out these infinities and provides a framework where quantum gravity may be possible. The mathematics of string theory, however, demands more than the 3 dimensions of space we experience. For the equations to be consistent, additional spatial dimensions are required. In the simplest versions, there are 9 spatial dimensions, plus 1 of time, for a total of 10. Later, with the development of M-theory in the 1990s, the framework expanded to 11 dimensions. These extra dimensions are not visible in everyday life because they are thought to be compactified, curled up at scales far smaller than atoms, hidden from direct observation. We move freely through 3 dimensions because they are large, but the others are compact and inaccessible, like tiny circles at every point in space. The presence of extra dimensions may sound speculative, but it is not arbitrary. The mathematics of string theory simply does not work without them. In this way, the theory pushes us to imagine a reality richer than what our senses reveal. The 3-dimensional space we know is part of a larger geometric structure, one that may contain shapes and symmetries beyond ordinary experience. In some models, the shape of the compactified dimensions determines the physical constants of our universe, such as the masses of particles and the strengths of forces. Change the geometry, and the laws of physics change. This leads naturally to the idea of a string theory landscape. There may be an enormous number of possible ways to compactify the extra dimensions, each corresponding to a different vacuum state with different physical laws. The number of possibilities is vast, perhaps as large as 10 to the power of 500. If this is correct, then string theory does not describe one unique universe but a multiverse of possible universes, each defined by a different configuration of the hidden dimensions. Our universe is simply one choice among many in this landscape. Such a picture resonates with the inflationary multiverse of Level 2. Eternal inflation could generate bubbles that explore different regions of the string landscape, each with different constants. The multiverse, then, becomes not just a possibility, but an almost unavoidable consequence of combining inflation with string theory. What was once a theory of unification becomes a theory of diversity, predicting not one set of laws, but a vast ensemble of possible laws. This shift has been controversial, but it reflects the mathematics honestly. Beyond compactified dimensions, string theory also introduces the concept of branes, short for membranes. In this view, our universe may be a 3-dimensional brane embedded in a higher dimensional space. Other branes could exist parallel to ours, separated by extra dimensions we cannot access. Interactions between branes could even explain cosmic events. One proposal, known as the ekpyrotic model, suggests that the Big Bang might have been the result of a collision between branes in higher dimensions. This is speculative, but it shows how string theory expands the horizon of cosmology. The brane world picture opens extraordinary possibilities. If other branes exist, they may host their own universes with their own physical laws. These universes would not be spatially distant bubbles created by inflation, nor quantum branches of a wave function, but literally neighboring universes in higher dimensional space. Though separated from us, they could, in principle, influence our universe through gravity, which is thought to be able to propagate through the higher dimensions. Some experiments at particle accelerators and gravitational detectors have searched for such effects, though none have been found so far. The absence of direct evidence does not mean the ideas are empty. String theory is motivated by the need for a consistent theory of quantum gravity, a goal that has eluded physics for decades. Its extra dimensions and branes are mathematical necessities of the theory, not arbitrary inventions. While unproven, they are grounded in the same pursuit that produced relativity and quantum mechanics: the desire for a unified description of nature. Whether string theory ultimately succeeds or not, it has already transformed how physicists imagine the universe. It has shown that reality may be more than three-dimensional space, and that our universe may be part of a larger structure beyond our perception. The introduction of branes adds an entirely new dimension to the discussion of the multiverse, both literally and conceptually. If our universe is a three-dimensional brane floating in a higher dimensional space, sometimes called the bulk, then it is natural to ask what else might inhabit that bulk. Just as multiple sheets of paper can exist side by side without touching, multiple branes could exist in parallel, each carrying its own universe, with its own particles, forces, and histories. These universes would not be connected to us by any ordinary means, since all of the matter and energy we know is confined to our brain. The only force that might bridge between branes is gravity, because in string theory, gravitons, the hypothetical particles of gravity, can move through the higher dimensional bulk. This possibility means that evidence for other branes, if it exists, might appear as gravitational anomalies. If gravity leaks into extra dimensions, its strength at short distances could deviate from the predictions of Newton's law. Experiments have tested gravity at millimeter scales with exquisite precision, searching for deviations that might signal the presence of extra dimensions. So far, none have been found, but the search continues. Even a small deviation could be a sign that our three-dimensional brane is part of a larger, higher-dimensional reality. The ekpyrotic scenario takes this idea further. Proposed in the early 2000s, it suggests that the Big Bang itself may have been the result of a collision between branes. In this model, branes drift in the higher dimensional bulk and occasionally collide. The enormous release of energy from such a collision could ignite a hot, dense state, similar to the one we call the Big Bang. Instead of a singular beginning to time, the universe may undergo cycles of expansion, cooling, and brane collision, producing an eternal sequence of cosmic rebirths. While this scenario remains speculative, it offers an alternative to inflationary cosmology and shows how string theory can inspire new approaches to fundamental questions. The brane world picture also offers insights into one of the deepest puzzles in physics: why gravity is so much weaker than the other forces. Electromagnetism and the nuclear forces operate with great strength at atomic scales, while gravity is feeble, only becoming significant when masses are astronomical. String theory suggests that gravity's apparent weakness may be an illusion. If gravitons can travel into extra dimensions, while other forces are confined to the brane, then gravity's influence is diluted. This could explain why it is so much weaker in our universe compared to the other forces. Again, experiments have searched for evidence of such leakage, but none has yet been found. The sheer number of possible universes predicted by string theory is staggering. The string landscape, with perhaps 10 to the power of 500 possible vacuum states, means that the theory does not predict one unique set of laws, but an enormous variety. This has been both a strength and a weakness. On one hand, it offers a natural explanation for why our universe has the values it does. We are in one of the rare configurations that allow life. On the other hand, it makes the theory difficult to test, because if almost anything is possible, then predicting specific outcomes becomes harder. Some critics argue that this makes string theory less scientific, because it risks becoming unfalsifiable. Supporters reply that the landscape is a real feature of the mathematics, and avoiding it would be dishonest. In this way, string theory reflects the tension between uniqueness and multiplicity. Physicists once hoped that a theory of everything would explain why the laws of nature are as they are, uniquely and inevitably. String theory suggests instead that the laws may be environmental, one choice among many in a cosmic landscape. If this is true, then the task of physics is not to explain why the constants have their particular values, but to explain why we find ourselves in one region of the landscape rather than another. The answer may lie in anthropic reasoning. We are here because only here can observers exist. The anthropic principle, though controversial, becomes harder to ignore in the context of the string landscape. If universes with different constants exist, then it is no surprise that we observe a universe compatible with life. It does not mean that life was the goal of the universe, only that life can only arise in universes where conditions allow it. Critics argue that this explanation is unsatisfying because it does not predict specific values, but it does provide a framework for understanding why the universe appears fine-tuned. At the same time, string theory has deepened our understanding of mathematics and physics, even without direct experimental confirmation. It has inspired connections between geometry, topology, and quantum field theory. It has led to breakthroughs such as the ADS-CFT correspondence, which links a gravity theory in higher dimensions to a quantum field theory without gravity in lower dimensions. These insights have advanced physics in unexpected ways, showing that even speculative theories can produce fruitful results. The vision that string theory and M theory offer is bold. Our universe is not an isolated domain, but one surface in a higher dimensional space. Other surfaces may exist, parallel to ours, inaccessible, except perhaps through the faint tug of gravity. The Big Bang itself may have been a brain collision, one event in a larger cosmic cycle, and the constants of nature may be environmental, one set among countless others in a vast landscape of possibilities. While none of this is proven, it is rooted in serious efforts to unify physics. It is not myth or pseudoscience, but the extension of mathematics to its logical implications. As we follow this path, we encounter the concept of infinity once again. If the string landscape contains more possibilities than there are atoms in our universe, then the multiverse is not just large, but infinite in its scope. Infinity introduces profound challenges, both mathematical and philosophical. To understand them, we must turn from the specifics of string theory to the broader issue of infinity in physics. String theory and M theory remain among the most ambitious scientific projects ever attempted, aiming not just to describe a part of nature, but to unify all forces and particles into a single coherent framework. Their predictions of extra dimensions, brains, and an immense landscape of possible universes expand our vision of reality far beyond what classical cosmology imagined. Yet with this expansion comes a confrontation with infinity. The number of possible compactifications of extra dimensions, estimated at values like 10 to the power of 500, is so large that it effectively functions as infinite for all practical purposes. When every possible arrangement of constants and forces can exist somewhere in the multiverse, how do we make sense of probability, prediction, and scientific explanation? This is the heart of the challenge known as the measure problem. In a finite universe, probabilities are straightforward. We can count outcomes, compare frequencies, and make predictions. In an infinite ensemble of universes, however, every possibility occurs an infinite number of times. If every outcome is realized infinitely often, how do we say which outcomes are more likely? How do we define probability when everything that can happen does happen, over and over again without bound? This problem is not only mathematical but philosophical, cutting to the very foundations of what science means. The string theory landscape intensifies this problem. If universes with every possible set of constants exist, then our universe is one among them. But what does it mean to predict anything? If the answer to every question is that all outcomes happen somewhere, then how can science retain its power to explain? Some physicists suggest that probabilities in the multiverse must be defined by measures that weight different kinds of universes differently, but there is no consensus on how to do this. Others argue that the multiverse is a description, not a predictive theory, and that physics must continue to seek deeper principles. Even with these challenges, string theory has reshaped how physicists think about fundamental reality. The discovery of dualities, surprising mathematical equivalences between seemingly different theories, has revealed that physics may be more unified than it first appears. For example, the ADS-CFT correspondence shows that a gravity theory in higher dimensional space can be equivalent to a quantum field theory without gravity in lower dimensions. Such insights have not only enriched our understanding of string theory, but also provided powerful tools for studying black holes, quantum entanglement, and condensed matter systems. These connections show that even speculative theories can yield concrete progress. The dream of a final theory, one that unifies all forces and explains all constants, remains unfulfilled. String theory is a candidate, but its vast landscape suggests that uniqueness may not be achievable. Instead, the theory points toward a reality where multiplicity is fundamental, where universes with different laws coexist in a higher dimensional framework. This vision may be unsettling because it challenges the expectation that nature is uniquely determined, but it also expands our imagination, forcing us to confront a cosmos more diverse and complex than we ever imagined. In the absence of direct experimental evidence, string theory remains provisional. The Large Hadron Collider and other experiments have not yet found signs of supersymmetry, which many versions of string theory predict. Gravitational wave detectors have not revealed hints of extra dimensions. The mathematics of compactification is far from fully understood, but none of these uncertainties diminish the importance of the theory as a guide to what might be possible. Just as quantum mechanics was once a strange, untested framework that later revolutionized physics, string theory may hold insights not yet visible. What it has already done is to remind us that the universe may not be what it seems. The 3 dimensions of space we know may be only part of a deeper geometry. Our universe may not be the whole, but one brain among many. The Big Bang may not have been the beginning of everything, but a collision in higher dimensional space. And the constants of nature may not be uniquely determined, but drawn from a vast landscape of possibilities. These are profound shifts in perspective, born not of myth, but of mathematics. The path now leads us directly into the concept of infinity. Inflation, many worlds, and string theory all point toward realities that are not just large but boundless. The mathematics of infinity enters into physics in ways both necessary and troubling. To continue the story of the multiverse, we must now pause to examine what infinity means in mathematics and cosmology, and how physicists attempt to tame it. Infinity is not just a philosophical abstraction, but a feature of the equations themselves, one that raises paradoxes and challenges at the very frontier of science. Infinity is one of the most powerful and unsettling concepts in science. It appears simple at first glance, as the idea of something without limit. Yet when examined closely, infinity is layered with paradoxes, mathematical subtleties, and physical implications that reach to the heart of cosmology. In the context of the multiverse, infinity is not an optional curiosity, but an unavoidable feature. Eternal inflation, quantum branching, and the vast string landscape all imply realities that may be infinite in scope. To understand these ideas, we must first confront what infinity means. In mathematics, infinity is not a number, but a concept describing unbounded growth. The simplest version is the infinity of counting. We can count 1, 2, 3, and so on without end. This is called a countable infinity. Georg Cantor, the 19th century mathematician who first formalized the mathematics of infinity, showed that not all infinities are equal. The set of integers is infinite, but the set of real numbers, which includes all decimals, is a larger kind of infinity. Between any 2 integers, there are infinitely many real numbers, and Cantor proved that the infinity of the reals is uncountable, larger than the infinity of the integers. This discovery was astonishing, showing that even infinity has structure and hierarchy. Infinity in physics is both a tool and a challenge. Calculus, the language of modern science, relies on infinite processes, such as limits and series. Without infinity, there would be no way to describe motion, fields, or waves. Yet physical infinities often signal trouble. When a calculation produces an infinite result for a measurable quantity, it usually means the theory is incomplete. The appearance of infinities in quantum field theory, for example, forced the development of renormalization, a mathematical method to remove divergences and produce finite answers. Similarly, the singularity at the center of a black hole, where density becomes infinite, is widely believed to indicate the breakdown of general relativity. Infinity in equations is often a sign that new physics is needed. In cosmology, infinity arises naturally. If space is infinite, then the universe extends without bound in all directions. If time is infinite, then the cosmos has no beginning or end. If inflation is eternal, then universes continue to form forever. Each of these infinities carries profound consequences. An infinite space implies infinite repetition, where every possible arrangement of matter occurs somewhere. An infinite time implies that events, no matter how improbable, eventually occur. An infinite multiverse implies that every possible universe exists, not once but endlessly. These conclusions may seem more like philosophy than science, but they flow directly from physical theories taken seriously. The problem of probability becomes acute in an infinite cosmos. In a finite universe, we can assign probabilities based on relative frequencies. But in an infinite multiverse, where every outcome happens infinitely often, how do we define what is likely? This is the measure problem of cosmology. Different ways of regulating infinity lead to different answers, making probability ambiguous. For example, if there are infinitely many universes with observers like us and infinitely many without, how do we decide which is typical? Without a clear measure, predictions in the multiverse become slippery. Philosophical paradoxes sharpen the issue. One famous thought experiment is the idea of Boltzmann brains. In an infinite cosmos with random fluctuations, it is inevitable that self-aware brains could spontaneously assemble from chaos, complete with false memories. In fact, given enough time, such brains may outnumber ordinary observers. If so, why are we not Boltzmann brains? Another paradox is the duplication problem. In an infinite universe, there must be exact copies of you somewhere else, living lives identical in every detail. What does identity mean if it is repeated endlessly across infinity? These puzzles are not fantasies but logical consequences of infinite ensembles. Despite these difficulties, infinity is hard to avoid in modern physics. Inflation, quantum mechanics, and string theory all point toward it. Some physicists attempt to sidestep infinity by proposing finite models, such as cyclic universes or compact spaces. Others embrace infinity as a fundamental feature, seeking new ways to define probability and typicality within it. Either way, the issue cannot be ignored. Infinity shapes how we think about the multiverse and whether its predictions can be made scientific. The challenge is to handle infinity with rigor. Mathematics gives us tools to distinguish between types of infinity, but physics requires us to decide which infinities are real. Is space truly infinite, or just very large? Is time eternal, or does it have an end? Are the infinities of string theory literal, or artifacts of incomplete understanding? These are not abstract questions, but ones that shape our models of the cosmos. Infinity is where mathematics and physics meet philosophy most directly, and so, the exploration of infinity leads us back to the limits of science itself. To ask about infinite universes is to ask about the boundaries of what can be known. It is here that the multiverse confronts its greatest challenge. To proceed further, we must see how physicists have attempted to grapple with infinity and how it complicates the search for evidence of other universes. Infinity is both a necessity and a burden in cosmology. The necessity comes from the mathematics of expansion. If inflation occurred, and if it is eternal, then the number of universes it produces is infinite. If space itself is flat, as measurements of the cosmic microwave background strongly suggest, then it extends infinitely in all directions. These are not optional assumptions, but natural outcomes of the best models we have. The burden comes from the fact that infinity complicates prediction. Science advances by comparing theory with observation, but in an infinite ensemble, any observation is guaranteed to occur somewhere. If every possible outcome is realized infinitely many times, then how can one outcome be used to test a theory? This dilemma is called the measure problem. To make predictions in an infinite multiverse, cosmologists must introduce a way to regulate infinity, a cutoff that allows probabilities to be defined. One approach is to impose a finite time cutoff, counting events up to a certain cosmic time and then letting the cutoff grow. Another approach is to use a spatial cutoff, counting within a finite volume. Yet these methods can produce wildly different answers, depending on how the cutoff is chosen. For example, some measures predict that we are overwhelmingly likely to be Boltzmann brains, random fluctuations in a chaotic infinity. Others predict that ordinary observers like us are typical. The lack of consensus shows how difficult it is to tame infinity in physics. The paradox of Boltzmann brains illustrates the strangeness of infinite reasoning. Ludwig Boltzmann, the 19th century physicist who developed statistical mechanics, suggested that the universe's low-entropy state might be explained as a rare fluctuation in a larger equilibrium system. But in an infinite universe, the most common fluctuations would not produce entire universes but small structures, such as isolated brains that briefly flicker into existence with false memories. If the universe is infinite and eternal, then Boltzmann brains vastly outnumber ordinary beings. If so, the fact that we perceive a coherent history becomes paradoxical. Why are we not one of the countless random fluctuations? This is one of the reasons physicists suspect that infinity must be handled carefully or avoided if possible. Another puzzle comes from duplication. In an infinite universe, every arrangement of atoms must occur somewhere. That means there are regions of space, unimaginably far away, where copies of Earth exist, identical in every detail. There are copies of you, reading these words, living lives indistinguishable from your own. This is not science fiction, but a consequence of probability applied to infinity. The number of possible arrangements of matter in a finite volume is finite. Given infinite space, those arrangements repeat. The duplication problem raises questions about identity, free will, and meaning. If there are infinitely many versions of you, then what does it mean to say that you are unique? Cosmologists acknowledge these paradoxes but do not see them as reasons to abandon theory. Instead, they are clues that our understanding of infinity is incomplete. Some argue that infinities in physics should be viewed as signs that the theory has reached its limits, just as infinities in black hole singularities suggest the breakdown of general relativity. Others argue that infinity may be real, but that we must refine our definitions of probability to handle it. Both approaches require humility, for infinity pushes science to the boundary of what can be formalized. Infinity also enters into the physics of black holes. The singularity at the center of a black hole is a point of infinite density, where space-time curvature diverges. Most physicists believe that this infinity is not physical, but a sign that general relativity must be replaced by quantum gravity at extreme scales. Similarly, the Big Bang itself begins with a singularity, an apparent infinity of density and temperature. Again, most believe this is a limit of the theory rather than a literal infinity. These examples show that while infinities appear in equations, they often mark the frontier where new physics is needed. Still, there are forms of infinity that may be unavoidable. The uncountable infinity of real numbers underlies calculus and the entire framework of physics. The concept of infinite time or space may be real if the universe is flat and eternal. The question is not whether infinity exists in mathematics, it clearly does, but whether it exists in physical reality. That distinction is crucial. Mathematics can describe infinities of many sizes and shapes, but physics must decide which of those infinities are realized in the universe. The difficulty of infinity in cosmology is not only mathematical, but philosophical. If infinity guarantees that all possibilities are realized, then explanations lose force. To say that something happens because it is inevitable in an infinite ensemble may be true, but it may not satisfy the human desire for understanding. Science seeks to explain why the universe is as it is, not just to say that every universe exists somewhere. Infinity can seem to drain explanations of meaning, yet at the same time, it opens vast horizons, showing that reality may be far richer than any finite picture allows. The multiverse forces us to confront infinity directly. In eternal inflation, the number of universes is infinite. In quantum mechanics, the branching of many worlds is infinite. In string theory, the landscape of possible vacua may be effectively infinite. Infinity is not an optional assumption, but a central feature. To proceed, physicists must develop ways to work with it, to define probability, typicality, and meaning within it. Only then can the multiverse become more than a philosophical possibility. Infinity is not only a mathematical curiosity, but a challenge that shapes the way we think about the cosmos. It is embedded in our equations, in the predictions of cosmology, and in the very structure of theories that attempt to unify physics. Yet handling infinity requires more than calculation. It demands careful thought about what is real, what is an artifact of mathematics, and what can be observed. One strategy physicists use is regularization, a way of cutting infinities down to size in order to extract finite results. In quantum field theory, infinite quantities often appear in intermediate steps, but with renormalization, these infinities can be absorbed into redefined parameters, leaving predictions that match experiments to extraordinary precision. This shows that infinity can be managed in practice, even if it never disappears from the theory. But in cosmology, the infinities are not just in the math, they are in the physical picture itself. An infinite space, infinite universes, infinite time. Regularization cannot so easily rescue us here. Another approach is to argue that infinity is a sign that we have gone too far. Just as the singularity in a black hole is likely a sign that general relativity has reached its limit, infinities in cosmology may signal that our theories of space and time are incomplete. Perhaps the universe is finite but vast, or perhaps time is finite though unbounded, like the surface of a sphere extended into 4 dimensions. These possibilities remain open. They remind us that infinity, while elegant in mathematics, may not be realized in nature. Still, infinity has proven extraordinarily useful. Without it, there would be no calculus, no physics, no predictions of planetary motion or electromagnetic waves. Infinity is not the enemy of science, but one of its most powerful tools. The challenge is knowing when infinity is a tool and when it is a claim about reality. That boundary is difficult to draw, but it is where the most important questions lie. For cosmology, the question is pressing. If the universe is infinite, then everything possible happens. If eternal inflation is correct, then an infinite number of universes are being born, even now. If string theory is correct, then the number of possible vacuum states is so large as to be indistinguishable from infinite. In each case, infinity is not just a number, but a framework for reality. Accepting it changes how we think about probability, uniqueness, and explanation itself. The paradoxes this creates, such as Boltzmann brains and duplication, are not trivial. They force us to consider what it means to be an observer in an infinite ensemble. They remind us that physics is not only about equations, but about meaning. If explanations collapse under the weight of infinity, then perhaps our theories must be refined. If infinity is inescapable, then perhaps our understanding of explanation must change. In either case, infinity pushes us to the frontier of both physics and philosophy. As we step beyond infinity, we move from theory into the search for evidence. If the multiverse is real, can we detect it? Can we find traces of other universes in the cosmic microwave background, or in gravitational waves, or in the physics of black holes? Or are other universes forever beyond observation, leaving us only with theory and speculation? These are the questions that define the next stage of the journey. From mathematics and paradox, we turn to experiment and observation, searching for the faintest hints that we are not alone in the multiverse. The idea of a multiverse is bold, but for it to be considered seriously in science, it must connect in some way to observation. Theories gain power not from imagination alone, but from their ability to make predictions that can be tested. Yet if other universes are separated from us by cosmic horizons, quantum branching, or higher dimensional brains, then how could we ever detect them? The challenge is immense. By definition, universes beyond our own may be inaccessible. But physicists have not given up. They have searched for indirect evidence, subtle signals that might hint at contact between our universe and others. One of the most promising places to look is the cosmic microwave background, the faint radiation left over from the Big Bang. This radiation carries a detailed record of the universe when it was only 380,000 years old. Its temperature variations across the sky, measured with increasing precision by satellites like COBE, WMAP, and Planck, reveal the seeds of galaxies and the fingerprints of inflation. If our universe had ever collided with another during its earliest moments, the impact might have left an imprint in this background. The idea of bubble collisions arises from eternal inflation. If inflation produces multiple universes, then bubbles of space may occasionally crash into one another. Such collisions, though rare, could leave circular scars in the cosmic microwave background, regions of unusual temperature or polarization. Physicists have scanned the microwave maps for such patterns, searching for concentric rings or cold spots that might signal an ancient collision. So far, no conclusive evidence has been found. The cold spot in the southern hemisphere of the sky, once suggested as a possible collision imprint, is now thought to be a statistical fluctuation, or perhaps the effect of a large cosmic void. But the search continues, because even one confirmed collision would revolutionize cosmology. Gravitational waves provide another potential channel. These ripples in space-time, first directly detected in 2015 by the LIGO Observatory, are generated by violent cosmic events, like merging black holes. But inflation also predicts a background of primordial gravitational waves, generated in the earliest moments of the universe. If bubble collisions occurred, they could have sent out gravitational wave signatures distinct from the inflationary background. Detecting such signals would be extraordinarily difficult, but future observatories, both on Earth and in space, may have the sensitivity to attempt it. Some scientists have even considered whether black holes could provide hints of other universes. Black holes are regions of space-time so warped that nothing can escape their gravity, not even light. At their centers, current theory predicts singularities, where density becomes infinite and our equations break down. Some speculative ideas suggest that black hole singularities might connect to new regions of space-time, perhaps even birthing new universes. While intriguing, this remains far beyond testable science. Observations confirm that black holes exist and behave according to general relativity, but no evidence shows that they are portals to other universes. The scientific consensus is cautious. Black holes are fascinating, but they are not gateways. These examples show both the promise and the difficulty of searching for other universes. The cosmic microwave background may carry hidden scars. Gravitational waves may hold subtle signatures. Black holes may hint at deeper structures. But each possibility faces immense challenges, both in theory and observation. The signals are faint, the data complex, and the interpretations uncertain. So far, no evidence has compelled scientists to accept that we have glimpsed another universe. Yet, even the attempt matters. The search for evidence keeps the multiverse within the realm of science, rather than leaving it entirely to philosophy. It reminds us that bold ideas must always be tested against reality, however difficult the test. And it shows that physics, even at its most speculative, is guided by the same principles that have always driven it. The desire to connect theory to observation, to let nature decide what is true. The search for traces of other universes in the cosmic microwave background has been one of the most direct ways physicists have tried to turn the multiverse into a testable hypothesis. The radiation itself is astonishingly uniform, varying only by about 1 part in 100,000. Yet those tiny variations carry profound information about the early cosmos. When mapped in detail by the Planck satellite, the microwave background revealed anomalies that sparked debate. The most famous is the so-called cold spot, a region of the sky cooler than expected. Some researchers proposed that this could be the signature of a collision between our universe and another bubble in the early inflationary epoch. Others suggested it might be caused by a vast underdense region, a supervoid, along the line of sight. As more data accumulated, the evidence favored the void explanation, though uncertainties remain. The lesson is clear. Searching for other universes requires great caution, because cosmic anomalies can have many possible causes. Another anomaly discussed in the data is the apparent alignment of temperature fluctuations in certain directions, sometimes called the axis of evil. If confirmed, such large-scale patterns could challenge the assumption that the universe is statistically uniform on the largest scales. Some scientists have speculated that this too might hint at influences from beyond our cosmic horizon, though most explanations remain within conventional cosmology. The debate underscores the difficulty. The cosmic microwave background is a single sky, a single dataset. Unlike particle physics experiments that can be repeated countless times, the cosmic background is unique. We must extract all possible information from one sample, which means distinguishing signal from noise is especially hard. Gravitational waves represent another frontier. When LIGO and Virgo detected the first gravitational waves in 2015, it opened a new window onto the universe. Most detections so far have come from astrophysical sources, like merging black holes and neutron stars. But cosmologists hope to one day detect a primordial background of gravitational waves, faint ripples generated in the first instance after the Big Bang. Inflation predicts such a background, and bubble collisions in a multiverse could amplify or alter it. Detecting these signals requires instruments even more sensitive than LIGO, such as the proposed space-based observatory LISA, or networks of pulsar timing arrays that can measure gravitational waves of very low frequency. These projects are underway, but it may take decades before they reach the necessary precision. If a distinct gravitational signature of a bubble collision were found, it would be one of the strongest pieces of evidence for the multiverse. Physicists have also considered whether particle physics might reveal clues. If our universe is one bubble in a larger landscape, then the values of fundamental constants, such as the mass of the Higgs boson or the strength of the cosmological constant, may reflect environmental selection. While this does not provide direct evidence of other universes, it strengthens the case for their existence as an explanation for why the constants take the values they do. The discovery of the Higgs boson in 2012 at the Large Hadron Collider confirmed a cornerstone of the Standard Model, but it also raised puzzles. The Higgs mass is precariously balanced, requiring fine-tuning that seems unnatural. Some scientists argue that this fine-tuning may be explained if many universes exist, and we happen to live in one where the Higgs mass allows stable matter. This is not experimental proof, but it shows how the multiverse can function as a framework for interpreting puzzles in fundamental physics. Still, the absence of direct detection cannot be ignored. Unlike galaxies or black holes, other universes do not send light or gravitational signals that we can easily observe. The cosmic horizon is a real boundary, not just a technological one. No matter how advanced our telescopes, we cannot see past the speed of light barrier. This makes the search for other universes fundamentally different from most scientific quests. The evidence, if it exists, must be indirect, subtle, and deeply embedded in the structure of our own cosmos. This raises an important question about the nature of science itself. Can a theory be considered scientific if it predicts entities that may never be observable? Some argue yes, if those entities are natural consequences of theories already supported by evidence. For example, if inflation is strongly confirmed, and if eternal inflation is a natural outcome of the equations, then bubble universes may be considered a legitimate scientific inference, even if they remain unobserved. Others disagree, arguing that without the possibility of direct or indirect testing, such claims belong to philosophy rather than physics. The debate continues, highlighting the tension between theory and evidence at the frontier of cosmology. The pursuit of evidence has not been fruitless. Even when no signs of other universes are found, the searches refine our understanding of cosmology. Mapping the cosmic microwave background has confirmed inflation's predictions with extraordinary precision. Gravitational wave observatories have opened a new era of astronomy. Particle colliders have revealed the properties of fundamental fields. Each step advances science, even if it does not prove the multiverse. The very act of searching ensures that the idea remains anchored in evidence, not drifting entirely into speculation. As the search expands, scientists remain aware of its limitations. The cosmos may keep its secrets beyond our reach. Yet history shows that boundaries once thought impassable often yield to new methods of inquiry. Radio waves revealed galaxies beyond the Milky Way. Neutrino detectors uncovered processes in the heart of the Sunday gravitational waves now allow us to hear the universe as well as see it. Perhaps future generations will develop instruments sensitive enough to probe beyond our horizon in ways we cannot yet imagine. Until then, we continue to test, to refine, and to push observation to its limits. The search for evidence of other universes leads us into a paradoxical position. On one hand, science demands testability. On the other hand, the very nature of a multiverse may place most of its domains forever beyond our reach. The cosmic horizon is not an obstacle that can be bypassed with better telescopes. It is a boundary imposed by the finite speed of light and the finite age of the cosmos. Beyond it, no signals can ever reach us. If other universes exist outside this boundary, then they may be permanently hidden. This does not mean that the search is futile. Indirect evidence remains a possibility. Bubble collisions, if they happened, may have left scars in the cosmic microwave background. Primordial gravitational waves may carry faint echoes of inflationary processes. Subtle clues in particle physics may point toward environmental selection in a multiverse. Each of these avenues remains open, though none have yet delivered decisive proof. The difficulty lies in the faintness of the signals and the uniqueness of the data. We have one sky, one universe, one set of constants. Extracting evidence of other universes from this limited sample is extraordinarily difficult. Some scientists argue that the multiverse will never be testable and therefore does not belong within science. Others reply that science often advances by inference. We cannot see the interior of a black hole, yet we infer its existence from its effects on nearby matter. We cannot observe quarks directly, yet we confirm them through the results of particle collisions. In the same way, if a theory like inflation is strongly supported, and if it inevitably predicts multiple universes, then it is reasonable to infer their existence, even if we cannot observe them directly. The multiverse, in this view, is not a separate hypothesis, but a consequence of theories already tied to evidence. The debate touches on deeper questions about the philosophy of science. Should we require that every entity in a theory be directly observable, or is it enough that the theory as a whole makes testable predictions? If the latter, then the multiverse may qualify as science, even if most of its universes remain forever beyond observation. If the former, then the multiverse risks being classified as metaphysics. The boundary is not sharp, and throughout history, ideas once thought metaphysical have become scientific. Atoms, black holes, and gravitational waves were all speculative before evidence confirmed them. Perhaps the multiverse will one day cross the same threshold. For now, the search continues at the edge of observation. Cosmologists scan the microwave background for anomalies. Gravitational wave astronomers design detectors to probe the earliest instants of time. Particle physicists explore the limits of the standard model, for signs of deeper structure. None of these efforts guarantee success, but each advances knowledge in its own way. Even if other universes remain hidden, the pursuit sharpens our understanding of this one. And so we arrive at a point where physics meets philosophy. The multiverse may exist, but its evidence may be beyond reach. The question becomes not only whether it is real, but how we should think about it. Does the multiverse provide explanation, or does it dilute explanation by making everything inevitable? Is it science, or is it metaphysics? These are not merely technical questions, but philosophical ones, shaping how we interpret what science can and cannot say about reality. The transition is clear. Having explored the attempts to find evidence of other universes, we must now confront the philosophical dimensions of the multiverse. Physics may guide us to the edge of observation, but beyond that edge lies a landscape of reasoning where philosophy has always played a role. To continue the story, we must step from telescopes and detectors into questions of meaning, explanation, and the limits of knowledge. When scientific theories push to the very edge of observation, philosophy enters naturally. The multiverse is one such case. Inflation, quantum mechanics, and string theory all point toward the possibility of multiple universes, yet direct evidence remains elusive. In this gap between theory and data, philosophy helps us examine the meaning of these ideas, the logic of their explanations, and the limits of science itself. To understand the philosophical dimensions of the multiverse, we must ask what kind of explanation it offers, whether it satisfies or undermines our need for understanding, and how it interacts with principles like Occam's razor, which cautions against unnecessary complexity. One of the strongest motivations for considering the multiverse is the problem of fine-tuning. The laws and constants of our universe seem delicately balanced for complexity. The strength of gravity, the value of the cosmological constant, the masses of fundamental particles, small changes in these quantities would produce universes hostile to life. If gravity were slightly stronger, stars might collapse too quickly. If the cosmological constant were much larger, galaxies might never form. Why should these numbers fall in the narrow range that allows complexity to exist? Some interpret this as evidence of design, others as coincidence. The multiverse offers another option. If there are countless universes with different constants, then it is no surprise that we find ourselves in one that allows life. This reasoning is called the anthropic principle. In its weak form, it states that we can only observe conditions compatible with our existence. In its stronger form, it suggests that the universe must have properties that allow life to exist. Otherwise, we would not be here to observe it. Within the multiverse framework, the anthropic principle becomes a selection effect. Out of countless universes, only a few allow life, and we are naturally in one of those. The multiverse, then, shifts the question from why the constants have the values they do to why we observe them as we do. The answer is that only in such universes could observers exist. This explanation has both power and controversy. It is powerful because it removes the need for deeper fine-tuning. Constants need not be uniquely determined by fundamental laws. They can vary across universes. Life does not require a cosmic purpose. It requires only a suitable environment. But it is controversial because it seems to explain by deferral. It does not predict specific values. It simply states that values compatible with life will be observed. Critics argue that this weakens the explanatory power of science, shifting from prediction to selection. Supporters reply that it is still an explanation, one that fits naturally with the idea of multiple universes. Philosophy also helps us examine the role of Occam's razor in the multiverse debate. Occam's razor advises that we should not multiply entities beyond necessity, that simpler explanations are to be preferred. Does the multiverse violate this principle by adding countless universes? Some argue that it does, that invoking an infinity of unobservable worlds to explain the values of constants is extravagant. Others argue that it does not, because the multiverse is not an extra assumption, but a consequence of theories already supported. If eternal inflation is correct, then bubble universes follow. If many worlds is correct, then branching follows. The multiverse may be the simpler explanation, requiring no special rules or fine-tuning. Whether it violates or fulfills Occam's razor depends on how one interprets simplicity. Another philosophical issue is the boundary between physics and metaphysics. Physics is based on testability, the ability to confirm or refute claims by observation. Metaphysics addresses questions that go beyond observation. Where does the multiverse fall? If it is a consequence of inflation, quantum mechanics, or string theory, then it may belong within physics, even if most of its universes cannot be observed. If it cannot be tested even indirectly, then it may belong to metaphysics. The line is not sharp. Throughout history, concepts once considered metaphysical, like atoms or black holes, became scientific once evidence was found. The multiverse may one day do the same. The philosophical implications of the multiverse extend beyond explanation and method. They touch on meaning and perspective. If there are countless universes, then our universe is not unique. If every possible history is realized, then our choices are one path among many. For some, this is liberating, showing that existence is abundant and diverse. For others, it is unsettling, making life seem less significant. Philosophy helps us navigate these reactions, reminding us that significance is not diminished by multiplicity, and that meaning is shaped by perspective as much as by cosmology. The multiverse also challenges the idea of ultimate explanation. If every possible universe exists, then there may be no deeper reason why our universe has the properties it does. The explanation is that it is one of many. Some philosophers see this as the end of inquiry, while others see it as a new beginning. The multiverse may not explain why mathematics exists, or why there is something rather than nothing, but it reframes those questions in a broader context. Instead of seeking a single necessary universe, we confront a vast ensemble where possibility itself is realized. The anthropic principle, though often invoked in multiverse discussions, sits uneasily in the philosophy of science. Its weak form is almost tautological. We observe conditions suitable for observers, because if conditions were not suitable, we would not be here to observe them. This is logically true but not very informative. The stronger form, which suggests that the universe must allow for observers, raises further questions. Must implies necessity, but is the existence of observers necessary in any scientific sense? Or is it simply a reflection of the fact that in a sufficiently large multiverse, some universes will inevitably contain observers? The strength of the anthropic principle is that it can address the fine-tuning problem without appealing to hidden purpose or deeper laws. If the cosmological constant were even a few orders of magnitude larger, galaxies could not form, and yet, in the string theory landscape, many universes may have such large constants. We live in one of the rare universes with a small constant, because only such universes allow galaxies and life. This reasoning was famously applied by Steven Weinberg in the 1980s, who predicted that the cosmological constant should be small but non-zero, close to the upper limit for galaxy formation. Later measurements of cosmic acceleration confirmed that the cosmological constant is indeed small and non-zero, within the range he anticipated. For supporters, this was a triumph of anthropic reasoning within a multiverse framework. But critics argue that anthropic explanations lack predictive power. If any value of a constant is possible in the multiverse, then the anthropic principle only tells us that we will observe one compatible with life. This is true, but it does not uniquely predict the value we see. It cannot be falsified, because whatever we observe can be explained as necessary for observers. In this way, critics worry that anthropic reasoning risks turning science into circular reasoning. The debate over whether this constitutes explanation or evasion remains unresolved, highlighting the difficulty of applying philosophical principles in cosmology. Occam's razor also cuts both ways in this debate. To some, the multiverse is extravagantly complex, postulating countless unseen universes when one universe should suffice. To others, it is simpler than fine-tuning. If the laws of physics allow multiple universes, then refusing to accept them would be an unnecessary complication. Simplicity is not always about the number of entities, but about the economy of assumptions. Which is simpler, a single, finely tuned universe, or a multiverse, where tuning is unnecessary? The answer depends on one's philosophical taste as much as on the data. This highlights an important point. The multiverse is not only a scientific proposal, but also a philosophical one. It forces us to clarify what we mean by explanation, simplicity, and testability. It pushes us to consider whether science is limited to what can be observed, or whether it can also include logical consequences of theories we trust. These questions are not new. They echo debates in the philosophy of science going back to the early modern period, when natural philosophers argued about the role of unobservable atoms, forces, and fields. What counts as legitimate science has always evolved as evidence and theory advance. The multiverse is simply the latest frontier. Another philosophical question is whether the multiverse satisfies or undermines our desire for ultimate explanation. For centuries, scientists have sought laws of nature that are universal and unique. The dream of a theory of everything is that it will explain why the laws are as they are and could not be otherwise. The multiverse seems to deny this dream. If all possible laws are realized somewhere, then there is no ultimate explanation. Our laws are one set among many, selected by chance or necessity in a larger ensemble. Some philosophers and physicists find this unsatisfying, a retreat from the ambition of science. Others accept it as the natural outcome of progress, a recognition that reality may be richer than any single law could describe. Philosophy also reminds us that the multiverse cannot escape metaphysical questions. Why is there something rather than nothing? Why are there laws at all? Why does mathematics describe reality so well? The multiverse does not answer these questions. It only reframes them. Instead of asking why our universe exists, we ask why any universe exists. Instead of asking why our laws are as they are, we ask why there are laws at all. The multiverse may provide context, but it does not end inquiry. If anything, it deepens it, pushing us to confront the foundations of existence. In this way, the philosophical dimensions of the multiverse are not a weakness, but a strength. They reveal that cosmology is not only about observation, but also about meaning. They show that science and philosophy are not separate but intertwined, each informing the other at the limits of knowledge. The multiverse, whether real or not, forces us to confront what it means to explain, to know, and to exist. The question of whether the multiverse belongs to physics or metaphysics is not easily answered. It depends on how we define science itself. If science is limited to what can be observed directly, then the multiverse lies outside its boundaries. But if science is about constructing theories that explain what we observe, even if those theories entail unobservable consequences, then the multiverse remains within reach. Atoms were once unobservable, yet they were accepted because they explained patterns in chemistry and thermodynamics. Black holes were once invisible, yet they were accepted because they explained the dynamics of stars and galaxies. The multiverse may follow the same path, gaining legitimacy as a natural consequence of theories that succeed in other domains. This does not mean that philosophy becomes unnecessary. On the contrary, philosophy plays a crucial role in clarifying what counts as explanation, what counts as simplicity, and what counts as testability. It reminds us that science is not only a body of knowledge but also a method shaped by deeper assumptions. The multiverse brings these assumptions to the surface, forcing us to articulate them clearly. It makes us ask whether our desire for uniqueness and necessity in the laws of nature is a principle of science or a preference of the human mind. For many, the multiverse also reshapes questions of meaning. If countless universes exist, then our universe is not central, but one of many. If every possible history unfolds somewhere, then our choices are not unique, but one path among infinite branches. This can be disorienting. That's the port, LA 50. It may seem to diminish significance, reducing life to a statistical inevitability. Yet another view is possible. Multiplicity does not erase meaning. The fact that other universes may exist does not diminish the value of this one. Significance is not measured by uniqueness, but by experience. Even in a vast multiverse, the life we live remains real and precious. The philosophical tension lies between explanation and mystery. The multiverse explains fine-tuning, but at the cost of introducing vast ensembles. It satisfies some questions, but leaves others deeper. Why this ensemble rather than none? Why mathematics at all? These are questions that may never yield scientific answers, but they remind us that the frontier of cosmology is also the frontier of human thought. The multiverse is as much an invitation to philosophy as it is to physics. And so, at the boundary between evidence and speculation, physics and metaphysics, explanation and meaning, the multiverse stands as one of the most provocative ideas of our age. Whether it is true or not remains uncertain. What is certain is that it challenges us to rethink our place in reality, to question the nature of explanation, and to accept that science may not provide closure, but instead open ever wider horizons. From here, our story turns outward once again, into the realm of imagination and culture. Long before cosmologists formalized the multiverse, poets, writers, and storytellers dreamed of infinite worlds. The idea has seeped into literature, philosophy, and modern media, shaping how we imagine existence itself. To understand the impact of the multiverse, we must now step beyond physics and philosophy into culture, where infinite dimensions have inspired wonder for centuries. Long before physicists proposed mathematical models of multiple universes, human imagination had already ventured into that territory. The idea that reality could extend beyond a single cosmos has appeared in myths, religions, philosophies, and stories for millennia. The multiverse in culture is not identical to the multiverse in science, yet the resonance is striking. Where physicists speak of inflationary bubbles, quantum branching, or higher dimensions, imagination has spoken of hidden realms, parallel worlds, and endless cycles. Both reflect a deep human instinct to wonder whether what we see is all there is. In ancient Hindu cosmology, the universe is not singular, but cyclic. Sacred texts describe vast cycles of creation and destruction, with universes arising, lasting for billions of years, and dissolving again, only to be reborn. These visions bear a striking resemblance, in spirit if not in detail, to modern ideas of eternal inflation or brain collisions. In ancient Greece, philosophers like Democritus and Epicurus proposed that infinite space must contain infinite worlds, some like ours, others utterly different. During the Renaissance, Giordano Bruno imagined that the stars were suns with their own planets and inhabitants, a vision far ahead of its time, and one that anticipated the modern discovery of exoplanets. In literature, the multiverse has long been a metaphor for possibility. Jorge Luis Borges explored infinite branching realities in The Garden of Forking Paths, a story that mirrors the logic of the many worlds interpretation of quantum mechanics. Science fiction has expanded the idea even further. Stories of alternate histories, such as Philip K. Dick's The Man in the High Castle, imagine worlds where events turned out differently. Modern films and television have embraced parallel realities as central themes, often using scientific terms like wormholes, quantum fluctuations, or higher dimensions as narrative devices. Though dramatized, these depictions reflect genuine scientific concepts, and they have carried the multiverse into the popular imagination. Popular culture often emphasizes the emotional dimension of the multiverse. Characters encounter alternate versions of themselves, confront lives they might have lived, or glimpse worlds where tragedy was avoided. These stories resonate because they mirror universal human questions. What might have happened if we had chosen differently? And how much of our lives is determined by chance? The multiverse provides a framework for exploring freedom, destiny, and regret in ways that are both imaginative and accessible. At the same time, science communication has embraced the imagery of the multiverse, blending cultural metaphors with rigorous physics. Physicists such as Max Tegmark and Brian Greene have written for general audiences about the levels of the multiverse, bringing abstract mathematics into vivid language. Documentaries and lectures frame inflation, quantum mechanics, and string theory as not only technical theories, but also sweeping narratives about the scope of reality. Cultural familiarity with the multiverse helps these ideas take root in the public mind, while cultural portrayals in turn shape how the public interprets scientific work. The exchange, however, is not without risks. Fictional portrayals often depict multiverse travel as effortless, with characters stepping across dimensions as easily as opening a door. In science, by contrast, universes are separated by insurmountable horizons, or coexist only as branches of a quantum wave function. These simplifications can blur fact and speculation, leaving audiences uncertain where science ends and storytelling begins. Yet even with distortions, cultural portrayals have value. They make complex ideas tangible, they spark curiosity, and they encourage people to engage with physics who might otherwise ignore it. The deeper reason for the cultural appeal of the multiverse lies in psychology. Human beings are drawn to stories of multiplicity because they reflect the uncertainty of life. Every decision closes some paths and opens others. Imagining that alternate versions of ourselves live those paths allows us to explore possibilities without losing the life we know. It is both a mirror and a release, a way to grapple with the consequences of choice and chance. In this sense, the multiverse functions as a cultural symbol as much as a scientific hypothesis, embodying the tension between determinism and freedom. Imagination has always been a partner of science. Before telescopes revealed galaxies, poets and dreamers imagined other worlds. Before relativity described curved spacetime, artists conceived of elastic, shifting geometries. The multiverse continues this tradition, inspiring both speculation and wonder. Science provides the equations, culture provides the narratives, and together, they give us a richer way to think about existence. Whether or not the multiverse exists, it already lives in our collective imagination. It shapes how we tell stories, how we interpret our choices, and how we conceive of reality itself. Culture and science, in dialogue, keep the idea alive, rigorous in equations, vibrant in stories, and profound in the questions it raises about meaning. From this cultural landscape, we return at last to science, where the multiverse remains an open question. Theories suggest it, imagination embraces it, but proof remains elusive. As we turn to the final chapter, we face the deepest uncertainty. What do infinite dimensions truly mean? And can such a reality ever be known? The multiverse stands at the edge of science, a concept both daring and unsettled. Inflation, quantum mechanics, and string theory each point toward the possibility of multiple universes, yet none provide decisive proof. The idea may be a natural consequence of our best theories, or it may lie beyond the reach of testability forever. At this frontier, physics meets philosophy, and certainty gives way to open questions. One of the most fundamental questions is whether the multiverse is testable at all. For a theory to belong to science, it must connect to observation. Yet by definition, most other universes would remain beyond our cosmic horizon. Some argue that indirect tests are possible. If inflation is confirmed with greater precision, and eternal inflation follows from its equations, then bubble universes become a legitimate inference. If the Schrödinger equation is truly universal, then quantum branching follows from taking it literally. If string theory's landscape is real, then countless vacua exist as a consequence of its mathematics. Others remain unconvinced, insisting that, without observable signatures, such ideas risk drifting into metaphysics. The open questions extend into each theory. Inflation explains much of the cosmic microwave background, but its cause and its ultimate fate remain unknown. Quantum mechanics makes flawless predictions, but its interpretations from collapse to hidden variables to many worlds remain unsettled. String theory provides a candidate for unifying gravity and quantum mechanics, but it has yet to find experimental confirmation, and its vast landscape raises the problem of whether uniqueness is lost. All three frameworks confront infinity, a concept that sharpens paradoxes. In an infinite multiverse, every possibility occurs infinitely many times. How then can probability be defined? How can prediction remain meaningful? Philosophy highlights the tension. The multiverse offers an explanation for fine-tuning by invoking multiplicity, yet some see this as evasion rather than understanding. Occam's razor is wielded in both directions. Some argue that countless universes are extravagant, others that denying them requires unnecessary assumptions. At the deepest level, the multiverse challenges the idea of ultimate explanation. If every possible law and constant exists somewhere, then why this universe? Why these laws? Why anything at all? The question is dissolved rather than answered. For some, this is unsatisfying. For others, it is liberating. The significance of the multiverse is not only scientific but also human. If countless universes exist, then our world is not unique. If every possible history plays out, then our choices are one path among many. This can feel disorienting, as though meaning itself is diminished. But significance need not depend on uniqueness. Our lives matter because they are lived, because they are real in this universe. Regardless of what else may exist, multiplicity does not erase value, it reframes it. In the end, the multiverse is not a final answer, but an invitation to deeper questions. It shows us that the universe may be larger than we can ever know, that infinity may be built into the fabric of reality, and that explanation itself may have limits. Whether or not it is true, the multiverse has already expanded our imagination, blending physics, mathematics, philosophy, and culture into one of the boldest visions of existence ever conceived. To contemplate infinite dimensions is to stand at the edge of knowledge, where science and wonder meet.